All right, everyone, welcome back. In this video, what I'm going to do is talk about capacitors. Now, I think capacitors can be kind of confusing to think about, so hopefully I can break this down in a way that's very clear. Now, the way a capacitor works is you have these metal plates, and what happens is when you apply a voltage, what's going to happen is at first you're, of course, going to have a difference. So at first you're going to have 0 volts measured across this capacitor, because there's no difference in potential energy. They're just metal plates that have some amount of electrons, but we can just assume that basically there's no difference in potential energy along them. And as we apply a voltage across this capacitor, so now we turn on our voltage source or a battery, we now have that 9 volts basically being, at first we have 0 volts being applied across this capacitor, and now what happens is we have current flowing, and I'm going to draw current in the correct direction so that way it's clear what's going on here. So you have current flowing, and remember that current is just the flow of electrons or the movement of electrons. So what's going to happen is in the metal you're going to have these electrons moving, and they're going to start accumulating on this side of the plate, and this is going to be the negative side of the plate, and this is going to be the positive side of the plate. So you'll have an electron appear here, and 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 et cetera, et cetera, et cetera. And what's going to happen is, if these plates are close enough together, there's going to be some distance here. We often call this distance epsilon between the two plates. Because there's some negative charges here, there are going to be electrons in the metal on the other side of the plate that are like, well, screw this. I don't want to be around these other guys. I want to be out of here. So they're going to leave. The electrons are going to start leaving, and you're left with positive charges, or the absence of electrons, on the opposite side of the plate. Now, the thing to remember is if I plot this as a function of time, and this is the sort of, now what I want to do is sort of calculate the voltage. This is V of t as a function of time. What's going to happen is at first there's not going to be any potential difference across the plates. But as electrons start accumulating on this side, what's going to happen is there is going to start to be a voltage over time. And the way this voltage curve is going to look is actually something like this. Now, why does it curve down like this? Or why does it kind of flatten out over time? Well, what happens is putting the first electron on the plate is fine. It's easy to do. And the second and the third, over time. But as you start getting a lot of electrons on here, it becomes harder and harder to add additional electrons. And why is that? Because these electrons don't like each other. They're trying to basically repel each other, and adding another electron, finding space for it, it's really, really difficult. One professor I talked to, he compared this to trying to get people to come to a faculty meeting. It's like the more and more you try to get in there, the more and more resistance you're going to have. So basically what happens is it's harder and harder to get additional electrons on the plate because the plate is kind of getting saturated, and that's exactly what we see over time. So how does this relate to our water analogy? Well, the first thing to notice is as this voltage sort of levels out, as the voltage in this capacitor goes from 0 volts to 9 volts, what's actually going to happen is the current is going to go down. So the current's going to start because you're going to have movement of electrons onto the negative side of the plate, and then the movement of electrons from the positive side of the plate around the wire. So at first you're going to have quite a bit. In fact, I can even show what this would look like. At first, if I plot t and I plot my current, let me just go ahead and do this, and I plot I of t, at first you're actually going to have quite a bit of movement, but what's then going to happen is it's very, very quickly going to decrease. In fact, maybe it's better if I let's just say I draw it like this. Maybe at first you have a lot of current, and then eventually over time it just becomes harder and harder to add additional current, and this ends up being kind of what we see, something like this. So this is indeed what happens. Now, you're never going to exactly get to 0, but it really will kind of slope down like this. Now, the analogy with water that I want you to think about is, imagine we have this water capacitor unit, and it basically is this thing that has this elastic or rubber sort of barrier between these two parts. So as you start pushing water through, what ends up happening is it pushes up against the elastic, and water is flowing into the pump. And what starts happening is the elastic starts bending, so you still have water flowing through the pipes. You still have water going into the pump, but what ends up happening is it encounters more and more resistance as the rubber is sort of stretched, and eventually it gets to this point where it just kind of stops. It'll kind of stretch out, and then it'll just kind of be stuck like this. And oops. And as this happens, basically the plate is going to just be, here, I guess this rubber unit is just going to be there, and there's not going to be any flow of water. So it's actually going to eventually stop the flow of water as this rubber piece stretches out to its sort of maximum place. And then now all the pressure that's being generated by the pump is actually used to basically hold this elastic. It's basically counteracting the force of the elasticity of this thing. And ends up being what you see. So there's no more flow because all of that water pressure is being used up to keep this elastic in its place. And similarly with the capacitor, all that voltage that you're generating from the battery is actually being used to sustain a voltage difference across the plates of a capacitor. Now, how do we write this, or how do we understand what's going on here? Well, there's this nice way of remembering this called Eli the Iceman. And what matters here is the ice part. In a capacitor, and this is the C part, current leads voltage. So current I, and then E is sort of your potential energy or your voltage. So what happens is, of course, is your current starts out high. Notice here your I of t, and your voltage starts out low, and then over time your current goes down and your voltage goes up. And there's a really nice, nifty way to talk about the relationship with these that we see in a capacitor, and it goes like this. Your current as a function of time is equal to your capacitance times the derivative or the rate of change of your voltage. And this should intuitively make sense. Basically what happens is, of course, current is related to the change as the movements of electrons. So as the voltage across the capacitor starts to level out, if you look at this tangent line at any given point, what you're going to start seeing is it starts out pretty big, which is what we see here. But then as time goes on, as it becomes harder and harder to add additional electrons to the plate, this starts flattening out and you start going down to zero. So this is exactly what you see. And similarly, we can use the fundamental theorem of calculus and use this to solve for our voltage. Our voltage, V of t, equals 1 over c times the integral from minus infinity up to time t of, let's just create a dummy variable, I don't know, I of z dz, which is just a dummy variable we're integrating out. And let's just assume that at minus infinity, we have to assume that it's 0 at minus infinity up until some finite time. Otherwise, this thing just blows up. But that's just an assumption we make, and that's fine. That's what we're always going to sort of make. So this is pretty much the relationship that we see here, and this is how we plot it. Now, we'll talk later about why derivatives and integrals introduce this type of phase shift in these particular things. I don't want to get into the weeds on that yet, but suffice it to say for now, the understanding that I want you to have is that the way capacitors actually induce a change in the relationship between voltage and current due to the actual mechanics of the capacitor itself, and it can be captured very niftily in these integral derivative types of equations, which we will find ways to solve that don't involve having to solve these differential equations. So that's a preview of things to come, but hopefully with this you get an intuition or an idea of why it is that capacitors have this special relationship between voltage and current. So thanks for watching. In the next video, we'll talk about inductors.